All right, well, thanks very much. I appreciate the opportunity to come and share with you some of the work that we're doing to improve information for the power grid in response to geomagnetic storms. So I'd like to take a few slides here in the front to just talk about some of the motivation behind this work and give you a little bit of a trace of this topic in the policy discussions, both in industry and also in government. Then we'll jump into an overview of cause and effect stuff that you probably know already pretty well, but I just want to remind all the steps in the chain of cause and effect there. Then we'll jump into the importance of the geoelectric field as a key parameter that the power grid needs to understand how space weather is impacting the system. We'll jump into some details here on how geoelectric field calculations work, just starting with some simple assumptions, and then I'll briefly show you how that gets generalized to more realistic types of models. Then I'll shift gears and we'll talk about an end-to-end data flow system that we've put in place at Space Weather Prediction Center, both what we have today near to operational status, as well as a parallel system we have in development that incorporates some newer Earth modeling information. We'll touch briefly at the end on some validation studies we've been doing with a power grid out in the East Coast, and just a real short discussion about forecasting. I don't have too much results-wise on that because we've just started that work, but I'll show you one comparison that we have. This project actually is very much an interdisciplinary project. We've had to bring in expertise from other areas. I'm not really a geologist by training, so we brought in folks from the U.S. Geological Survey to cover the Earth conductivity modeling part. We've also gotten some help from the NASA CCMC on this, and they have some experience there. Also, the Canadians have a lot of experience with power grid and space weather effects, and they've provided some really important advice for us. We rely on data provider agencies, both from the US and Canada, to do the mapping project. And we've also we use an algorithm that the Finnish Meteorological Institute developed. Also at the end, when I mentioned some of the conductivity upgrades that we're looking at, this was results from the National Science Foundation EarthScope US Array project that we're using. Okay, so thinking about space weather and the power grid, we do know that a severe space weather storm is going to occur at some point in time. I can't think of anything that's a more prime example of critical infrastructure than the electrical power grid. There are so many other parts of our critical infrastructure that depend on reliable electrical power. We know that there were a wide number of impacts in March 13, 1989, including a power blackout in the Hydro-Quebec province, a transformer damage, lots of anomalies. And so there's a question of what happens when the next severe storm hits. So in order to look at this, understanding this, like I said, is an interdisciplinary kind of topic. It has both some applied research aspects, and also this area here is kind of drives a lot of use-inspired basic research. I think there's a lot of research modeling observational projects that really derive their inspiration from this kind of societal impact. So this is kind of the practical end of it. From policy, one of the key steps here was a workshop held by National Academy of Sciences, outlining kind of a worst-case scenario for a 1921-like storm, describing pretty catastrophic kinds of impacts. Subsequent reports sort of question these numbers, but they all agree that there's uncertainty, that we really don't understand the risk that well, and that this is an important risk to understand and to get a handle on. The Department of Energy and North America Electric Reliability Corporation held a workshop in November 2009 to both identify these risks, realize that there's a lot of work that needs to be done to really understand it, and this led to the formation of a geomagnetic disturbance task force by the Reliability Corporation. And that task force has pushed forward the understanding quite a bit over the last 10 years. There is another agency in government, the Federal Energy Regulatory Commission, that issued an order out to the standards groups requiring standard operating storm procedures. and also requiring a standard for doing vulnerability assessments. So basically, this commission is requiring all of the operating entities to do an assessment and find out how would they survive a 1 in 100 year storm, and if they do have problems, if they would lose a transformer or if they would have a collapse of voltage, to develop mitigation plans. So this was issued by the Federal Energy Commission. And there were some follow-on orders as recently as last fall to elaborate some of the further details here. In response, the Reliability Corporation that sets standards for the whole industry put together a standard operating plan for all the operating entities, and also put out a transmission planning standard in December 2014, addressing those requirements from FERC, and those are intended to respond to the requirement for system stability assessment, transformer modeling, and you can see there's also been updates recently to that standard due to this kind of back and forth between FERC and NERC in terms of putting out the details of how the grid should be able to respond to these events. Also, in the Office of Science and Technology Policy, the issue was highlighted in a strategy and action plan a few years back. This includes benchmarks for reduced geoelectric fields, so it's asking all the government agencies to work together to define what is the most severe storm that the grid should be able to withstand, and also calls on the agencies to improve the modeling and prediction of these impacts on critical infrastructure. Also calls for improving the magnetotelluric survey information that gives us all the earth conductivity information that we feel that we really need to do this calculation, and also for improving the Geomagnetic Observatory network. And there have been updates to this as well as recently as last March. In addition, executive orders have come out both in the past and the current administration, and I won't dwell on that too much other than to say that the current administration is also on board with protecting the grid against these kinds of events. Okay, so shifting gear, cause and effect. As we all know here, I presume, this all starts back at the sun with coronal mass ejections. They propagate from the sun to the earth, interact with Earth's magnetosphere, driving enhanced current systems in the magnetosphere and ionosphere. And in particular, all these currents contribute to the dB/dt that we see on the ground, basically the time-changing magnetic field time series. The primary current system that's inducing these currents in the grid, though, is really the Aurora electrojet system. So ultimately, this shows up as a time series magnetic field on the ground that we can measure. For example, there on the upper right panel is March 1989, measured at the Ottawa Observatory with horizontal components. Then basically the Earth conductivity acts as a frequency-dependent filter and modifies that signal to produce what is a calculated geoelectric field here for that same storm shown over on the right. And to just give you a feel for numbers here, with this particular conductivity model, this comes out to a peak of about 2 volts per kilometer or so. That induced electric field then is kind of the key, because it drives currents in the conductors that are on the ground, and that's what's leading to the induced current in the grid that we're worried about. This effect was observed pretty quickly after artificial conductors were put out into society. Early telegraphs recorded some of these geomagnetic storms. You can find a trace of this all the way back to the 19th century. Not too long after the electrical power grid became into existence, severe magnetic storm came along in March of 2040, and lo and behold, there were an extensive list of disturbances on numerous systems, various voltage surges and power swings, and transformer circuits tripping. This is just kind of a long list of different published, pretty well documented incidents on the grid that have continued to occur over time, just because of the presence of the grid with these geomagnetic storms. To look at what's going on in the grid, this is kind of the key impact here. Basically, we have currents that are flowing into the windings of transformers, and instead of being on the regular cycle that a transformer is on, that exciting current goes beyond the normal level. At that point in time, the magnetic material has actually saturated while the current is still going up. And in that case, what happens is that you lose that back EMF from the windings, and then you end up getting a very greatly enhanced current here. You can see it's about a factor of 100 higher than it would normally be in the system. So that's kind of the key problem, is when the transformer saturates, you go into this half-cycle saturation mode. In addition to this highly enhanced current in the windings, you're getting a lot of harmonics that are going out onto the system. That can cause various equipment to trip, and it also may be harmful to some of the equipment, not expecting those harmonics. Also, there can be stray magnetic flux that's spreading out into the supporting conducting structures that's holding the transformer in place, and that can generate eddy currents, which can actually heat up the supporting structures. So these are all this is all kind of the core of how the power grid is impacted, is through the transformer saturation. This is an example of actual measurements during the October 2003 storm that you may be familiar with. There are actually two CMEs that came through. This is the KP index here, and you can see the severe storm for the first CME and then the second CME on the next day. Shown here is an actual measurement of neutral current going into a transformer up in the northeast, and we can see these currents well correlated with the storm activity, and also some of these currents are getting close to about 100 amps or so that are going into the neutral of the transformer. So it's just kind of a real example of what is going on in a transformer during a severe storm.
Those currents are actually measured in the grid, in the system.
Yes.
Specific system.
Yes. Right. Yep. Okay, so turning to then geoelectric field modeling and trying to address this, basically it's become clear to us at Space Weather Prediction Centers. It's probably been true for well over a decade, but the power industry really needs a better indicator than these global indices that are just giving you a very gross picture of how high the magnetic activity level is. Geoelectric field has really been identified as the key space weather parameter that's needed. We found this out of a space weather workshop that we had 8 years ago, where we actually had the users sitting around the table and pinned down that this was really an environmental parameter that is needed by the industry. Since the standards iterations have been going forward, this is referenced time and time again in the industry standards groups when they're discussing geomagnetic effects on the grid. So it's clear that the industry is looking for this as a way of characterizing the impact of these events. Also, it shows up in the National Space Weather Plan documents as well. The advantages here is that we're going to a local regional activity characterization, and we know that there's going to be significant differences depending on where the grid region is operating. And in addition, the geoelectric field is directly telling us how much induction hazard is being generated by space weather, whereas the indices really don't do that. How would this information be used? Once the geoelectric field is known, well, I shouldn't say it's not simple, but it is straightforward to calculate geomagnetically induced currents in the power lines. It does require realistic system modeling. And in fact, once the standards were issued for doing some of these vulnerability studies, a lot of the operators and companies found out that they really had to go out and do a lot of hard work to develop a realistic system model for the grid and get all the resistances going to ground and resistances along the lines, get that all cataloged and categorized. Once we can calculate GIC, we can compare that to measured GIC for validation. So there is a validation step, and this is actually an ongoing topic of work right now. Also, once the GIC is modeled in a system, for instance, for this benchmark type of storm, then they can look at their system stability and their transformer behavior and figure out what the impact is on their system. In addition, with system planning, this could locate problem spots and focus mitigation efforts. So they could either consider doing some hardening steps, which would be engineering prevention. Basically, there are transformers that are less vulnerable. It's rather expensive, but that is one way of making the grid less vulnerable. Also, some of the devices that trip off can be upgraded and modernized, and this is one way of making them less susceptible. Also, some systems, some folks, for instance, up in Hydro Quebec, have installed GIC blocking devices to block DC flow into their system, and that's another approach. Unfortunately, this has a little bit of a whack-a-mole effect in the sense that if I block it here, sometimes the GIC ends up going down to my neighbor's system. So it's something that really requires a full system perspective. And finally, that kind of analysis can also inform what a real-time response procedure might be to an E-field nowcast or forecast. So if they know ahead of time they're going to have a problem in a particular area at a certain level of activity, that can inform a decision to separate off, for instance, a part of the grid that they know will have a problem. The GIC calculation, just a little bit of detail here so you get a feel for it. I've shown a real simple power grid thing here just for discussion purposes where we have 4 different nodes. Basically what one does is integrate between 2 nodes to get the induced voltage that's between these 2 points by integrating along that line. So it's just the dot product of the E field along the direction of the line. And then that can be converted into a net induced current and actually into a nodal current at each of these nodes by basically add the amount of current flowing induced going in here and the amount of current induced going out here. And that basically gives us our induced currents into the nodes. Then this is balanced when these folks do the GIC calculation. This is balanced by outflows. The outflows are both going out to other nodes here. So there's basically a nodal admittance matrix here that captures how the current flows out of the nodes to the other nodes. And then there's also a grounding current here, which is expressed in terms of a grounding impedance matrix here, which is their earthing matrix. So that's basically a way of characterizing the whole system. So this is what that Kirchhoff law looks like in kind of a matrix sort of general form here. And then by inverting that, you've got the currents to the ground, and that's the thing that can be compared with an actual measurement on the system. So that's just to give you a feel for that. Of course, the grid has hundreds and hundreds of nodes, so there's a lot more in terms of the scale of that. Okay, and then the E-field calculation, I'll just kind of go through this with the simple assumptions here. One, we just start with Faraday's law, taking the curl of the first equation here and plugging in the second, and do the same thing for the magnetic field. You basically get this Helmholtz relation here. If we plug in the frequency form of that, we've got these relationships here. And then the key thing becomes comparing the conductivity with the frequency and the permittivity here to find out which regime we're in. When one is up in the atmosphere here, it's mostly a wave phenomenon. The conductivity is pretty negligible there. But when you get down below the Earth's surface, then it becomes a diffusion equation, and the conductivity really dominates in that area. So that's kind of the formalism there. The wave number relation in the air is sort of this classic thing that's well known, and then this is the wave number relation down below the Earth, which, down below in the Earth is here. And that, of course, has a real and imaginary part, so you get a decay of those waves with a certain skin depth. So when we look at the relationship between the magnetic field and the geoelectric field here with a very simple uniform Earth case, there's a boundary, of course, between those where the E field and the B field are continuous here, so I can solve either those relations below or above the surface, and once I take the coordinate here to z equals 0, I'll have a valid relationship between the magnetic field and the geoelectric field, which is what I need in order to calculate geoelectric fields. If I use this relationship, then if I basically use Faraday's law with the form of the wave number down in the Earth, I get this relationship then between the horizontal electric field component and the magnetic field component here at the surface, and that's basically the solution I'm looking for. So what we have then is essentially a relationship between the E field and the B field, and what you can see is that, as I said earlier, the Earth is acting in this case as a high-pass filter for the magnetic field, which is providing the input signal here. So folks in the solid Earth community refer to this as the Earth impedance, And again, overall scaling of the square root of the frequency here. So basically, as we go to more realistic conductivity profiles, this frequency dependence will become more complicated, but you'll still have this overall scaling with frequency to the 1/2. There's an alternate formulation here too, because if we look at this I omega mu hy here, that's basically dB dt in frequency domain here. So I can also express this transfer function as a low-pass frequency relating the time derivative of the B field to the E field. And that can be a very convenient formulation as which I use later on in this talk, which we'll see. And this can be generalized to more complicated impedances simply by dividing by the I omega mu. All right, and then just kind of want to walk through what we call a one-dimensional multi-layer model, where basically we model the Earth conductivity as layers of varying conductivity. So here's an example layer where we have a fixed conductivity between these two coordinate positions. And this basically goes forward as an inductive solution. So we suppose that we know what this low-pass transfer function is here at the bottom of the layer, where I'm taking the E field and dividing by dB dt, basically here. And then once I know that, I assume that I have these upward and downward propagating waves within the medium with constant amplitudes here. And basically then within the layer, using Faraday's law, I have this particular formulation using those upward and downward waves for the E field and taking the spatial derivative with Z. Then I divide within the layer the E field representation by the dB dt representation here. And when I reduce this by basically forming the ratio of the B coefficient over the A coefficient, so I just have the ratio of those guys here, then I have an algebraic form here, which I can flip around and solve for this, for the ratio of B over A. That's kind of done here after a few steps. Now, if I suppose that I already know what this quantity is here in the bracket at the bottom of the layer, I can just plug that in. So that's, with sort of convenience of notation, I just reduce that to this form here. And then I actually have a solution for this B over A ratio here. Once I have that ratio of the B over A with this alpha sub I, I can plug that back into the equation and then set my coordinate to the distance at the top of the layer, and I have this recursion relation. So basically, knowing the transfer function at the bottom of the layer, I can calculate the transfer function at the top of the layer. So knowing the bottom, I can calculate it at the top. You'll notice in this form here too that if I take the basically the coordinate of the bottom of the layer and just let it go unbounded off to infinity, this actually reduces to the uniform half-space solution for the low-pass transfer function. So it's all consistent with that formulation that we covered earlier. Okay, so my goal here is to try to get the low-pass transfer function at the surface, and then I'll have what I need to deduce the E field from dB dt. Basically, with the n layers here, I can solve for the transfer function at the top of the bottommost layer, and then calculate the next layer, and so forth, all the way up to the top. And that's how the 1D solution works. This is an example calculation. So here are different layer and layer thicknesses with different types of resistivities. And this is frequency going here, log of frequency going along this line here. A uniform Earth with a negative 1/2 dependence would be like this straight line here. And so this is the form of what that transfer function, low-pass transfer function, looks like for this particular model. And then I just have another example which I included because I used this in the March '89 calculation. So basically, I'm taking my B field, I'm finding out what its frequency spectrum is, and then I'm using this filter to change those amplitudes in a frequency-dependent way, and then I have my E field coming out the other end. Okay, this is March '89, just kind of in detail showing that calculation, and kind of already covered that, so I'll go through this quickly. All right, so that 1D formulation then, in general, looks like this. Basically, the horizontal components of the E field are related to the horizontal components of the B field through Here I'm showing it as the impedance. In general, those impedance take the following form, where we start getting some non-zero contribution from the on-diagonal components, and each of these is its own function of frequency here. How do I figure this out? I mean, I have a way of calculating this if I know the layers, but how do I get the more advanced way of representing the Earth conductivity? There's two approaches that we use. One is it is possible to derive just an empirical transfer function from a magnetotelluric survey. So these folks go out, spend a couple weeks in a particular location measuring B fields and E fields, and basically construct the relationship and frequency domain between the horizontal E field and B field components. We can also rely on our folks over at USGS, who are able to take that information, run it through some of the models that they have for the 3D Earth, and then forward calculate a 3D model too. So that's another approach for forward deriving these types of transfer functions. But the transfer function is really the key for me, and as an applications person, that's the thing that I will use, drawing on expertise from these other areas to do this calculation. Okay, so I'm just going to show a few transfer functions here, but I wanted to just discuss real quick the units I'm going to display it in. It is one way of representing this is called apparent resistivity, and basically if we flip this around for uniform Earth, the apparent resistivity is just what that uniform resistance is. So this is a way of comparing any given transfer function component to what a uniform Earth would look like, and that's the basic idea. So this basically normalizes out that frequency to the 1/2 dependence that's in the impedance that I talked about earlier. So we'll show you a comparison using apparent resistivity here. So this is one location, and I'm showing here in pink the 1D model that's appropriate for that location based on literature surveying, kind of this first level of conductivity models that we had out of the community. Now shown in the other colors are actually results from a magnetotelluric survey. The off-diagonal elements here, which match sort of the 1D model, are shown fairly close to the 1D representation here. So this is a place where 1D is a pretty good representation. The on-diagonal elements here you can see are quite a bit, this is log here, so these are quite a bit lower in magnitude. So this is a place where 1D is a reasonable approximation. However, there are other locations where you go out and do a survey and there's a pretty bad mismatch between what 1D model one would use in that area and what the transfer function is in this location. So this is a place where we'll need to upgrade our conductivities to reflect more realistic Earth conductivity. Yeah. It could be, because these surveys are done at like about 70-kilometer resolution, and the 1D models are very broad regions. So it could be that the 1D is valid in a more limited area. Yeah, so that could be part of it. Just to give you an idea about the surveys that have been done for the empirical transfer functions, it's all these red dots here basically is where we have coverage. And this is from the USA Array project, as well as some contributions from USGS down here in Florida. So we do have a gap in this region here where we don't really have this improved information, but at least it kind of gives you a feel for the resolution of empirical transfer function. Okay, so I'm going to shift now to what we're producing in our data pipeline today. This is basically the system that we have that's it's running on our national critical systems, and we plan to get this out operationally in a couple months here. The basic flow is to take magnetic observatories on the ground, and that gives me the horizontal magnetic field components. There's 8 USGS observatories contributing and 5 Canadian observatories near the US border that are contributed here. Put those through a detrending algorithm, and then we're using an interpolation algorithm to derive a B field time series on a 1/2 degree by 1/2 degree grid over the lower 48. And that's using a spherical elementary current system model from the Finnish Meteorological Institute. So we're just using that as one way. There are, of course, other approaches that could be done there, but that's one that we have working at this point. Then this runs through the geoelectric field calculation on a 2 degree by 2 degree grid with the 1D conductivity. So here At each of these grid points, I know from the interpolation what the B field time series is, and then I basically convolve that in real time with the filter that's appropriate for that particular grid point. Then those results go into a graphical map. It looks kind of like this. We put those results in our database in gridded data files and also disseminate in a GeoJSON format for users. And GeoJSON is a format that's pretty easy to overlay into other tools as well. So that's our system that we have today. We do have some gaps in our coverage in terms of those magnetic observatories. So this interpolation, there are some areas here where there's going to be some errors and then some uncertainties due to that. This is just a animation of the March '89 storm, just to give you a feel for one thing, how rapidly things change from minute to minute, although of course it's quite faster than real time. Also, early in the March '89 storm, we can see an intensification here right when the Hydro-Quebec outage occurred, is right in this window. And then later in the day on the 13th, you'll see how the oval kind of expands down. We actually get a broader range of impacts. I'll let that go through the end of the 13th here, so you can kind of see things expanding downward. But one thing you kind of see after watching these over a period of time is that there's just certain areas of the country that are more vulnerable, and no doubt that's due to the conductivity. This area here is very much an induction hazard area, and also along the east coast lights up quite a bit during these events. Okay, another couple hours here. We'll be at the end of the 13th. There's a substorm that expands down in this period here as well, right through in this time period here. So it gives you an idea of at least what these maps look like at an accelerated pace. Okay, and then on our development system, not quite ready for prime time, but we take that same interpolation algorithm, and now we do an E-field calculation using those transfer functions I was talking about. That's done actually at the location of where the survey site was carried out. And then once I have those E-fields on kind of an irregular grid, I interpolate that to a half degree by half degree grid. And then I generate a map that looks like this. And of course, the map kind of reflects where we have coverage for the surveys, so you can see that. And one of the things that pops out right away is that some areas agree and some areas are wildly different and will really call for an upgrade. This was a storm that we had back on June 8th of this year, just a couple weeks ago, showing at the same time the 1D result. And you can see this whole corridor along here where the survey data is highlighting much stronger geoelectric fields in this particular region. So it kind of shows the contrast. Well, on the other hand, there's other parts of the country that are not too far off from what the survey data would have. So there's definitely regions where things are more complicated, and we'll need a more complicated model to capture that. The other thing we have more in offline development here is using what the USGS 3D model. Basically, those folks doing the inversions and forward calculations provide that to me at a 0.1 degree by 0.1 degree grid. We're not quite sure what spatial resolution is really going to be required for this application, so our initial guess is to start with the spatial averaging to half degree by half degree, and then we'll go through validation with the user community to see if that's the appropriate smoothing or if we have to go to finer resolution or not. This just gives you a sample calculation that we did using one of these models here. I have a couple slides to give you at least a picture of what these models look like in terms of resolution, so we'll get to that in just a minute. So in terms of doing the validation work, I'm sorry, but yeah, jumping too far ahead. Okay, this is the basically the fine dots here is what a 0.1 degree by 0.1 degree grid looks like over North America, and the half degree by half degree is shown here with the larger dots here. So it gives you a little bit of a feel for the scaling that we're looking at. This is a result from the September 2017 storm using one of the 3D models, and it kind of smooths things out, which I think maybe you would expect from some of the modeling. But again, this is very much going to have to come out of validation work to determine which approach is the right way to do Earth conductivity. The geomagnetic field, just one slide here on this interpolation. This is an algorithm spherical elementary current system built by and Biljanin that we're using. It was developed, actually, USGS led the implementation development of this. This is running on our system. So we do have uncertainties on what the accuracy of this is as well. So that's one more factor that we have to worry about. This just shows a sample interpolation map, and it also shows you where these observatories are with the white squares here. We have one region here that's not well covered. I think I have a map. If you basically calculate distance of these grid points from the nearest observatory, there's a couple regions where we're more than 1,000 kilometers away from their nearest observatory, and so we're kind of data starved in terms of our observations in some of these regions. If I were to drop all points more than 1,000 kilometers, I'd have a big hole right here actually in my map. So it gives you a little bit of an idea of some of the coverage needs that are required really to improve on this. Okay, so I'm going to turn now to validation work. Basically, we have to do this in partnership with industry. The government agencies are basically feel that our responsibility is to specify the environment and do this geoelectric field calculation for these storms using various types of conductivity specifications. And then we rely on someone in industry to actually carry out the integration along their system. Those transmission lines can actually switch in and out at different times, so they actually have to have the real-time information on how in order to do that calculation. Once they've done that calculation to calculate the currents, then that can be compared to the measurements they have, and we can start doing some actual validation. These are a list of active collaborators that we have, and our expectation is that each of the regional entities will eventually need to participate in validating to see if we've got the correct results for their operating location. I'll show you one example here where basically we used different types of approaches using the survey data over in the East Atlantic region. We know that there's some kind of interpolation that you'd have to make between those MT surveys in order to find out what the E field is on where the power line is located. So we repeated this with different averaging and different interpolation schemes and see what the sensitivity is to that. This shows you survey sites in this area where we did the validation study. This is one approach where we just calculate the E field at the survey sites without any smoothing whatsoever. This is during the September 2017 storm. Here we've interpolated that to a half-degree grid, which is what I have in development right now in our systems. This is using the survey sites themselves, but doing a smoothing function. So basically taking a 100-kilometer radius around each point and averaging all those transfer functions together. And the idea there is we don't want to be thrown off if there's some local anomaly that's driving the E field too strongly. And then this takes the smooth and interpolated together, so it's sort of the next level of smoothing beyond that. You put these side by side, you can just kind of see the various levels of smoothing that have occurred from just doing the data directly, smoothing to a grid, and here's the 100-kilometer smoothing down here. So this is the result we had at one of the sites where the user had measurements, basically comparing calculated GIC here with the measured, observed GIC. With the 1D model, you got a wide disagreement here. The blue line over on the right is the time series that was observed, and then the model ones are the different colors here. And even using a nearest neighbor transfer function actually flipped the correlation negative. So what we found is that it was really important to interpolate between the sites in order to get a correlation that was reasonably decent between the calculated and observed. At least in that particular site in that location, we got one result where it looks like we might be on track. Okay, and then a couple quick slides here on forecasting. At Space Weather Prediction Center, we've got a geospace model that's predicting the state of the magnetosphere based on solar wind inputs. Basically, the CONOPS here is that we assume that what we're seeing at the solar wind monitor is what the magnetosphere is experiencing right now, and then take advantage of that propagation time to give us a lead time in terms of driving of the magnetosphere. This model, of course, is community and went through a selection process here. This just kind of gives you some numbers of the level of involvement here. There's 3 different components involved in it. And the idea here is that the model, part of the output of the model are ground perturbations down on the ground. And then for my part, once I have ground perturbations predicted on the ground, in principle, I could put that through the Earth filter and calculate E fields ahead of time. We've done that in one case, and like I say, this is very early work, so we don't have results just yet. But for the April 2018 storm, this is based on the observatory data here, and this is based on the geospace model here. And frankly, it's a little disappointing in terms of being able to predict this successfully. So we expect, the minute-by-minute fluctuations are probably not going to be that great. It could be that once we go look at a longer time window, or we look at coarser levels, there may be some predictive signal in the input, but it's an open problem for us to figure out what's the best way to use these predicted ground perturbations to provide some kind of predictive information about geoelectric hazard. So kind of wrapping up here then, the vulnerability of the power grid is a potential risk to society. It's being addressed by government and industry and regulatory groups. The key parameter in this is the regional geoelectric field, which is basically calculated by convolving the magnetic field time series with a frequency-dependent filter that's a function of Earth conductivity. The derivation of this Earth filter can be pretty complicated in regions with highly structured geology. And so the most appropriate way to model the geoelectric field is actually something that's an open topic for us. Once the geoelectric field is known, the amount of current can be calculated from a DC model of the grid components. And it's these induced currents that are causing transformers to go into half-cycle saturation, which really poses the main hazard to the grid and causes all these other effects. In partnership with USGS, NASA, and Canada, we're using some of the results from the solid Earth geophysics community. We're making forward progress on real-time maps. We at least have the data flow in place, and it's not too hard to really upgrade the conductivity specification as we learn more. And then in collaboration with the wider science modeling community, we're looking at ways to do this as a predictive product, but that's pretty early days on that right now. So thanks for your attention, and I'd be happy to take any questions.
I noticed that some of the transfer functions you were plotting as a function of frequency or period, they tend to maximize around 10 minutes or something like that. If I remember right, a few minutes maybe. And my question is, how important? Yeah. So, well, this was one.
Let me go back.
Yeah, that one you just showed. This one right there. That was what I was saying. I kind of saw a modest peak at the top panel there,
right,
around 1,000 seconds.
Right.
But so, I mean, what cadence do measurements need to be made in order to get the information to the grid operators?
Yeah, no, it's a great question, and I'm relying a little bit here on what I hear from meetings with the folks there. But my understanding from them is that basically from about 10 seconds and longer is the frequency domain that they're concerned about. So they're not really concerned with stuff that's going shorter than that per se, just because of it being more of a DC effect in the system. Yeah. I guess the other thing here too is that just generally there's a skin depth effect here. So higher frequencies are basically interacting with the shallower layers, and lower frequencies are with the deeper layers. And generally, the deeper layers are better conductors as the temperature goes up at lower elevation. So if you look at those 1D models, for instance, you'll see the conductivities go up quite a bit once you get down to the lower layers as well. So that could be part of what's going on here. But then there's the spectrum of the storm, which is unique in each case too. So it's hard to make a general statement. But yeah, right now, full disclosure, we're using 1 minute cadence for the input observation, output observation, but based on user requirement to get down to 0.1 hertz, we'll have to get down to a higher cadence.
And the comparison with the space weather modeling framework model, the Ionosphere model,
Right.
was that on that same cadence when you're doing
Yeah,
that?
that's 1 minute also.
1 minute.
Yeah, that's actually a good point. Yeah, that might be worth considering. Yeah.
So these MT surveys, which I don't really fully understand, do they get depth information, or is it just skin? You know, the first if you're using a borehole in a well, it might be a kilometer at most.
Right.
How do they get?
So the goal that they have is to be able to find out what the low frequency transfer function is, and then based on that, through an inversion process that's all geophysics and kind of not my domain, figure out what the structure is, at depth. In a sense, though, I'm kind of an end consumer of the transfer function, so even if they don't necessarily figure out exactly how that structure is laid out, we as users of the information don't really need to know that. Once we know what the transfer function is, I'm off and running in terms of calculating an E field. So I don't know if that does that answer.
I was curious to know more how these MT surveys work. What are they measuring? And is it just at the surface of the Earth, or is it actually?
They're measuring at the surface, and they have both a magnetic field measurement and an electric field measurement, and then just do that campaign over a period of a couple of weeks, and then basically from that, and this is where it's their expertise, not mine, but this is where they deduce what that transfer function is as a function of frequency. The project it falls under is IRIS. Um, there's an IRIS website that has these. They're sort of publicly available transfer functions, so you might be able to get more information there if you're curious.
You mentioned about the tool in development of from the Earth scope transfer function as well as the USGS 3D model. So what's the difference of these two transfer function or conductivity model?
So with the transfer function approach, we just use the results from the surveys directly, and we don't worry about what the structure is below the Earth. With the USGS 3D, what they've done is they have basically community models out of the Solar Earth geophysics community that are constrained to be consistent with those survey results, so that they actually have a 3D model of what the structures are below the surface. And then, again, this is their expertise, but then they forward calculate what the transfer function is based on that on a regular grid, and can do that actually down to 0.1 degree resolution. So it's an inversion of the MT data in terms of an solid Earth model.
And on the first one, just you directly get the impedance tension.
Yes.
And the second one, you get a conductivity model. Then you calculate the impedance tension and calculate electric field.
Correct. Yeah.
But the depth of this study presumably now also would have a much better understanding of the impact of a nuclear-induced EMP, wouldn't one?
Possibly. The frequency domain is higher, so they're related in terms of the grid model, and they're related in terms that there must be some impact of the Earth. But since the frequencies are so much higher, and again, that isn't something I've probed in depth at all, but that would be the difference.
I'm sure we would do that.
Yeah. Yeah.
Is your 1D model result available online somewhere? Like if I give you a time series of geomagnetic field calculation, is there any kind of software or tools which can output the geoelectric field?
So there might be two resources. I don't know them off the top of my head specifically, but the North America Electric Reliability Corporation, when they set up the standards for all the industry, also have resources there and tools for doing some of these calculations. That would be one place that you could potentially look. Also, our colleagues at the U.S. Geological Survey, and I haven't looked at this myself, so I'm not sure in detail what they've done, but my understanding is they have a Python version in Git source that's publicly available for doing some of these calculations. So you might be able to consult with folks at USGS to get their version.
So there are some public code available. So
There's some available. Yeah.
but for the other more complicated ones, they are under development.
Yes, that's under development.
Okay.
Yeah.
Thank you.
22 years ago, Roger Pearkin Jr. and I submitted a proposal to one of the first NASA NSF space weather opportunities, where we wanted to make an estimate on the commercial impact of power grid failures.
Yeah.
And it was sort of flatly rejected
Oh.
by NASA because they said that wouldn't possibly be a focus of space weather research.
Hmm.
So I feel vindicated in seeing that this indeed is a focus of space weather research. So this was really very interesting. Thank you.
Thank you.
How far they have come in the last 20 years. Space weather wasn't even of interest to them initially.
Yeah, I mean, one of the reasons was, of course, that NASA headquarters really hated Roger Pearkin Jr. because in his thesis he had done a study by just using publicly accessible material on the true cost of a space shuttle launch. And he ended up saying that it was between 800 million and $1 billion. And NASA was still selling